Today in this lecture we are going to discuss about the PCM receiver. We have already discussed in our previous classes about the PCM. So in this class we will discuss about the PCM receiver because we know that when we transmit the PCM signal and after propagation of a certain distance we need to have a regenerator or repeater so that the regenerator will again regenerate the noisy or contaminated signal again then transmit. So that is why before having a full detail of the PCM receiver, we will try to discuss regenerative or repeater first, because we know that the received signal have a noise. So to minimize the effect of noise, we add a regenerator or repeater after a certain transmission distance. The basic block diagram of the repeater is given in this format. Like if you have a signal, a PCM signal that is propagate over a certain distance, so after a certain distance you can see that noise has been added in the signal. So this signal is a noisy signal, or you can say that the signal contaminated with the noise. So this is a low level, so 0, and this is high level 1, and this is low level again 0. So this is the input to the amplitude equalizer, and then after that decision making. So we have a timing circuit which transmit the sampling frequency to the amplitude equalizer and the decision making device. When you pass the signal through the decision making device, and then the decision making device have the sampling frequency. So this sampling frequency is like a synchronized sampling frequency. Then after that we can have a clean signal, as you can see. So this is 0 1 and then 0. So this looks like a clean signal, or you can say that regenerated PCM signal. So what does A do? A block. So this is the amplitude equalizer. It equalizes the given signal, and the timing circuit works based on the sampling frequency f of s, and the decision making device outputs the clean version of input signal contaminated with noise. So the repeater used to enhance the propagation distance, because when a signal propagate over a long distance, it is distorted or disturbed because of a channel anomalies like noise due to the electronics and attenuation due to after covering some distance, or weather or something other like attenuations due to scattering or fading. For more distance, the signal attenuation can be something like this. Like if you do not insert a repeater or regenerator after a certain distance, like if you increase the distance, then the signal will look like this. So you can see in the signal there is a more attenuation. The signal is more noisy. So that is why it is better to insert a repeater or regenerator after a fixed threshold distance, so that we can have a better signal. Then the second is the block diagram of the PCM receiver. So the block diagram of the PCM receiver, the first one is the regeneration circuit that we have discussed upstairs. So again the noisy signal, so PCM signal plus noise will enter into the regenerative circuit, and then it will give the clean signal. And we know that it is connected with the pulsar generator, so which is synchronous with the sampling frequency, and the sampling frequency is given to the regeneration circuit and also serial to parallel converter. So when this data is given like 0 1 and then 0, so then we need a serial to parallel converter which convert the serial data into the parallel, like these. If these are 3 digits, so we have 3 lines, so this is a parallel data. And then after that we need a digital to analog converter, so it generates quantized output. So like you can say an example, a pulse amplitude modulator. So that's why you can say it's analog signal, because it generates a pulse amplitude modulator. And after that, because we are detecting the signal, we are reconstructing the information. So that is why we know that if we are at the On the receiving side, we usually use low pass filter, which is tuned to the low frequency, whose cutoff frequency is the low frequency. So when you pass the signal to the low pass filter, it will remove the unwanted signal, and then it will give you the message signal. But if you want to understand more detail about this, so we can have a diagram so of the analog signal. So this blue line or this continuous line is the analog signal, or you can say this is actual signal, and this is a stair type. So this is a stair type. This stair type is basically a 4-bit sample signal. Like if you say that the n is equals to 4, so the bits are 4, so 4-bit sample signals. And you can say if the 4 bits are 4, so L will be equals to 2 raised to power n, so which is 4, so that is 16. So you can see that you have a 16 level: 1 2 3 4 5 6 7 8 9 10, and you can do 1 2 3 4 5, and then 5 here, 10. So the levels are 16 here. So and then the red line, so this red line is basically the quantization noise, or you can say error. So that is the difference between the actual line. So this is the actual line and this is the quantized line. So that is the difference between these two lines. So this is the quantization noise that you can easily calculate. So that is single amplitude. So this side you have a time arbitrary signal. So we know that the 0 degree, 45 degree, 90 degree, and up to 360 degree. The error also depends on the number of levels that you have. So if you want to minimize the error, you can increase the level. So if you are going to increase the level, so it means that level also depend on the number of bits, because we know level is equals to raised to power n. So if you increase L, so it means that you also need to increase n. So if you increase n, so it means that you are increasing the data rate. So it means that if you are increasing the data rate, you also need to increase the bandwidth as well. So there is a trade-off between these two things, that how much error is can be accommodated and how much bandwidth is sufficient. So we have a few points here to discuss. The number of quantization level. So that is L. So L is equals to 2 raised to the power n. So if we have a more n, we need large bandwidth. So if the bandwidth is large, error will be decreased. For example, in this case, we have selected 4 bit, then the L will be equals to 2 raised to power 4, that is equals to 16. And we know the step size, which is equals to VH minus VL, high voltage minus lower voltage, or maximum level minus lower level, divided by the L, and L is equals to raised to the power n. The other point is mean error of quantization. So that is QE square, that we have already derived in our previous lecture, that how it comes from, that is QE square is equals to delta square divided by 12. That we have already derived in our previous lecture. If you want to understand this derivation, please you need to see our previous lecture, so that you can easily understand this equation. This other one a component is the SNR of quantization. So SNR of quantization is equal to 6.02 n plus 1.76. In some books, it's written like 1.8 plus 6n. So if this equation we have also derived, so if you want to understand, you can see our previous lecture to understand these equations. There are some other points that we can discuss in this lecture as well, like PDF or quantization error. So if we represent our function like a unit step function, so the step is from A to B and the amplitude is 1 over B minus A, then you can write the probability density function, probability density of this function, that is equals to 1 over delta. So 1 over delta, so this is the change, because that is the area under curve. So this is the 1 over delta when minus delta by 2 to delta by 2, when the q is in between these two levels. and elsewhere it is always 0, like you can see here. Elsewhere it is 0. And you can calculate the mean of the quantization, and we know the general formula for the mean or the expected value, that is x multiplied by its probability density function. And in this case we can calculate the mean, that is x is q, and the probability density function, that is 1 over del, that we have written above here like this. So dq, so 1 over delta is constant, you can take it out, and then you can take the integration of q, so that is q square by 2, and you can write the upper limit and then lower limit. So 2 is constant, so 1 upon 2 delta, and then you can insert the upper limit minus lower limit. So 1 upon 2 delta, that is delta square by 4 minus delta square by 4. So this will be cancelled with each other, and then the answer is 0. So mean of quantization is 0. And then variance of quantization. We know the quantization error, so variance, the formula of the variance is Ex square is equals to x square multiplied by the probability density function from minus infinite to infinite. So if we insert our values in this formula, we know that x is q and the probability density function is 1 over delta square. So q square 1 over delta, and then if you integrate this, 1 over delta is a constant, q square integration is equals to q3 divided by 3 upper limit minus lower limit. If you insert the upper limit and lower limit, you will end up with that variance or quantization error that we have inserted upstairs, that was del square by 12. So we know the number of samples is equals to 2 raised to power n, and if you want to calculate n, you can write this formula, take log on both sides. So n is equals to log to the power log to l, where l is based on the maximum amplitude. So like if your signal is something like this, so this is maximum value, this is minimum value, and then in between you are dividing the number of levels. So the range of the amplitude is x max to x min, and this is the levels, number of levels. And then you can define the variance, that is equals to delta, that is equals to delta square by 2. So that is 1 over 3x max whole square into 2 raised to the power n. And then the other quantity, you can say SNR. So if the signal is non-sinusoidal, so if the signal is non-sinusoidal, so the SNR is equals to input power divided by noise power. So input power is P, noise power is sigma Q square, and we have already calculated sigma Q square is equals to 1 over 3x max whole square 2 raised to the power minus 2n. So if you simplify this equation, you can say that 3p into 2 raised to the power 2n divided by x max whole square. So this is the SNR if the signal is non-sinusoidal. But if the signal is sinusoidal, then in that case you can calculate the SNR. SNR, we know that is this one. So 3p divided by x max whole square multiplied by 2 raised to power 2n. So say this equation is A. And we know that for sinusoidal, the input signal is usually x max sine omega mt or cos omega mt. And we know the formula of the average power, that is the amplitude square divided by 2. So that is x max square divided by 2 p. So if we insert this p in this equation, so we have 3 multiplied by x max whole square, and then divide by 2, and then divide by x max whole square. So you know x max square will be cancelled, and the remaining is 3 by 2 multiplied by 2 raised to the power 2n. So if you wanna write this term in term of dB, then you are just taking the 10 log 10 of 3 by 2 and 2n. So you can, using the logarithm rule, you can open this 10 log 10 3 by 2 plus 10 log 10 2 raised to the power 2n. So the answer of this one, 10 log 10 3 by 2, if you used calculator, the answer is 1.76 plus 2n into 10 log 10 2. because this is power. So we know that if it is power, then it will become in front of here a log. So that is equal to 20 n log 2, and we know that log 10 2, the answer, if you multiply with the 20, the answer will be equals to 1.76 plus 6.02 n. So this is for the SNR in dB. So you can write the SNR in dB. So that is 1.76 plus 6.02 n. So this is all, and then after that we will do some examples. So please keep in contact with us, and if you have any question, you can please write the question in the comment box. Thank you for watching the video.